Are you listening to me? Yeah, okay, okay, better now. So, so today we're beginning late, 15 minutes late, because there was this problem with the yellow line, okay? This is exceptional. So for those who face the problem with the yellow line and are late, okay, maybe you did a good calculation. For those that are just late with no regard to this problem, you are late and you should tomorrow leave 15 minutes earlier, okay? So you know how to do the calculation already. So you can get better and better, have no excuse tomorrow. Tomorrow we begin at 9, okay? But today we'll shift everything by 15 minutes, okay? Anyways, after in the last session, we'll have the poster session, and so we'll be able to begin the poster session during coffee break already, so it's not a big deal. So I know that I said to you to hang the posters, but yesterday it was a confusion, so they removed the supports. Who had hanged the poster yesterday? Raise your hand, really. You? Just one? You? Two? Who has hanged the poster yesterday already? Just, okay, so for those who had hanged the poster yesterday, they have removed, thinking that there were posters for the last session. So you just go to the secretary and ask them, where is my poster? And so it should be there, okay? And so you take and you hang again. Okay. Don't forget to sign the list. If you have not signed now, you sign in the end of the class. Okay, so fechar aqui, se pá. Obrigado. So let's just remember what we did last session. So in the last session, we said, okay, now we have a Hamiltonian that will allow me to explain how an electric charge described, whose position and momentum is described by quantum mechanics, will interact with electromagnetic fields described by classical electromagnetism, okay? So this is the so-called semi-classical model. The Hamiltonian was like that, a function of the vector potential and the scalar potential. Very well. We have worked a lot with this Hamiltonian. We have done some approximations. We have changed the gauge. We have been to the Goppert-Meyer gauge. And we have done the long wavelength approximation. And we got, in the end, to a Hamiltonian which had two parts. The first part is just the Hamiltonian of the hydrogen atom. I'm not writing it down again. And the second part is just the dipolar Hamiltonian, the interaction Hamiltonian in the dipolar approximation. So this is just a first order interaction term, which is minus d scalar with the electric field calculated in the position of the center of mass. That by now we'll take it as 0, and then when the center of mass will become a degree of freedom, we will insert it again. So now I will just take R equal to 0 as we did last time, okay? Very well. So who is D? D is the dipole, electric dipole operator. It's just Q times the charge of the electron times the position of the electron. If we write that the charge of the electron is minus the fundamental charge E, so we have this, okay? So this is the dipolar operator. Then we said, we discovered that the dipolar operator in the basis of the eigenstates of the hydrogen atom is purely non-diagonal. So it will only have non-diagonal elements. I have not said how to calculate them by now. You must imagine how to calculate, because we know this will become integrals of the wave functions fn of x, y, and z, but I have not talked about this. We'll take a look on this later, if we have time, I'm not sure, but maybe we'll take a look on this later. And now I just said, imagine two levels, one ground and one of higher energy, that have non-zero diagonal elements between them. So in the most general case, we can write the Hamiltonian We can write then the electric dipole operator as a number which I suppose real times the raising operator and the lowering operator that you have also seen with Johannes last time. So he has also called those operators in what he was doing. Okay. So and then we have we had the total Hamiltonian that we wrote as 0 h bar Rabi frequency. Oh, sorry, there is not this times cos of omega t, h bar omega 0 cos of omega t, and h bar omega 0. Okay, so this is the Hamiltonian, and we have solved the dynamics of this Hamiltonian. So we have solved the dynamics that this Hamiltonian imprints on a state that began in the fundamental level. So if we imagine that the atom now in a linear combination of the ground and the excited state, right? And if the atom has begun in the ground state, we have discovered how is the general state. That I will just write it back here, and we'll talk a little more about the state before continuing. It's sad that when we get a nice result and we don't get to discuss about it, right? So we didn't have time, so let's just talk about it a little bit. Okay, and then, so this is omega 0, the Rabi frequency, and the omega is the generalized Rabi frequency, which is a function of omega and of the detuning, light detuning. Remember, the light detuning is omega, is the difference between the frequency of incoming light and the frequency of the atom, okay? So, from that, we can discover the population of the excited state. This is just omega 0 squared divided by omega 0 squared plus delta squared sinus squared of omega t divided by 2. Okay? Very well. So, now I want to dedicate some time to understand this solution here. I imagine that a two-level system is present in almost, so in what lots of people here do. Maybe not everyone, but lots of people deal with two-level systems. A two-level system is very fancy today because a two-level system is a qubit, and there are very different examples of two-level systems. You can have, here we are representing, we are taking an atom with two electronic levels, and we are saying that this is a two-level system. This is true. You can also have the spin of a spin 1/2 particle as a two-level system, so it can be up or down. You can have the polarization of a photon that can be linear vertical or linear horizontal, or circular plus or circular minus. You can write in any basis as also a system, a two-level system, right? So you have several systems in physics that can be represented as a two-level system. Okay, so here we have a two-level system. A two-level system, the state of a two-level system, apart from a global phase, can be written as cos of theta over 2 in the state, here we call it G. No, I'm gonna invert. So, yeah, okay, no, I'm gonna get little like this. So plus e to the I phi sine of theta over 2 times e, okay? This is the most general possible representation of the state of a two-level system. Theta and phi for us here are just generic angles, okay, to represent this system. So you see that when I change theta, I change the relative weight of G and E. So this number passes from 1 to 0, and this number passes from 0 to 1. And the phi here allows me to change the relative phase between these two levels, okay? So apart from a global phase factor, so if you have a phase related to the G, you can put it in evidence, and apart from the phase factor, this is the most general state you can write, okay? Everyone agrees? A state like this can be represented, I think most of you know this, a state like this can be represented in the Bloch sphere, right? So you have a bijection between each state and each point in the sphere of radius 1. So any state can be represented in the surface of this sphere of radius 1, right? Parameterized by the angle theta and by the angle, so phi with respect to the x direction. Let's put it like this. This is the angle phi. Okay? So if I represent this state in the Bloch sphere, where is the ground state? Like the way that, as I have written? Normally you put the ground state down, yes, but I have written it wrong. Not wrong, but I have put it in the opposite way. So if you want, I can change, but I can do this for you. Okay, let's do this. But then I will put the phase in the other one. So let's change. So I'm gonna make sine of theta over 2. This is not very common. Huh? I'm doing this just for you. E to E phi cos of theta over 2E. Okay? And then, where is G? G is now below. It's when theta is equal to 100 pi. Theta is equal to pi. Sine of pi over 2 is 1. And so when theta is equal to pi, I am below. And when theta is equal to 0, this is 0 and this is 1. So this is the excited state. Okay? And so the equator of this sphere, what does it represent? Superpositions. Okay, so every point which is in the equator of this sphere have theta equal to pi over 2. Right? And so if theta equal to pi over 2, if I put it here, pi over 2, this is sine of pi over 4, which is 1 over square root of 2. Same here, pi over 4, 1 over square root of 2. And so in the equator, the states are like G plus e to the I phi e divided by square root of 2. So they are superpositions with equal weight, okay? Now, taking a look at what we have discussed, how do I create those superpositions? If I have now this two-level system is my atom. I want to create a the atom is initially in the ground state. I want to create a superposition of G plus E with a certain phase. How do I do this? Yeah, so you can say. Yeah, this is a Hadamard gate, yes, but how do I do in practice? I'm discussing a physical process, really. I send light, right? I send light and I do a pulse. Okay, I do a pulse. So what's the duration of my pulse? We have said this last. The duration of my pulse is pi over 2 seconds. I don't understand. Pi over 2 seconds? Exactly. So pi over 2 pulse means that the Rabi frequency, which, okay, so first of all, let's say we are in resonance. So our light has the same frequency as the natural frequency of the atom, okay? So let's say that we are in resonance, delta equal to 0, then omega is just omega 0, and then I need to do a time such as this is equal to pi over 2. Okay, so the time is not pi over 2, the time is pi over 2 omega 0, right? Okay. Omega 0 is a Rabi frequency, and you will learn how to calculate the Rabi frequency with respect to the intensity of light that I send in a few moments. Okay. So, but the Rabi frequency is proportional to the electric field of the light, incoming light. So I can adjust. How can I adjust the Rabi frequency? I adjust the light intensity. More intensity, more electric field, more Rabi frequency, less time to do the pi over 2 pulse, okay? Okay, but when I do the pi over 2 pulse, let's do the pi over 2 pulse here. Can I? So if I do the pi over 2 pulse here, if I put delta equal to 0, so if I put delta equal to 0, and so omega equal to omega 0, and the time equal to this time here, let me take out the delta. This time here, if we insert it there, we are going to have omega times t equal to pi over 2. So this is pi over 4, this is pi over 4, this is 0, this is pi over 4. What do I get? I get phi equal to e to the e delta t over 2. This is a global phase factor that I don't care. I can even remove. Delta is equal to 0, moreover, so no delta. So I just get 1 over square root of 2 let's multiply g plus, here I have 1 and 1 over square root of 2, so minus e. Okay? So what's the relative phase of the superposition in this case? What's this phi here? Yeah, it's minus pi over 2 or 3 pi over 2 as we prefer, right? Because e to the e 3 pi over 2 is equal to minus e. Okay, so I have not created the phase that I want. Actually, from my model, there's a specific phase going on, and I just tick to this phase, and this is what happened, okay? So how could I choose this phase? What happened is that I did this movement here. Okay? What? I can go out of resonance is a possibility, because if I go out of resonance, I will have this acquire phase here. This is one possibility. Another possibility is to choose the phase of light. So if I send just one light beam, so this light beam has a phase. Okay, so then it doesn't matter the phase. This phase is just the phase, it's not really important thing, but if I send 2 different light beams, then I will have 2 different Rabi frequencies, and remember that the Rabi frequency is equal to d scalar with A0 over h bar. So the phase of the electric field that I send is going to give the phase of omega 0. So I can, if I have 2 different beams, I can allow the phase of omega 0 to be, omega 0 to have a phase. And if I allow omega 0 to have a phase, then I can control with beams of different phases, light of different phases, I can control the superposition. So indeed, I can let some detuning, or I can have different beams with different phases, and the phase of the light will be imprinted in the phase of the superposition. Okay? But indeed, the detuning is the most efficient solution. So if you let a detuning, so if you do like this, and then you let the light with small detuning, so this can evolve here, and then if you apply again a pulse, it's going to be in a different phase. Okay? So you can change the state of this 2-level system, which is ground and excited state, by applying light, and you can, by detuning the light, you can let the phase of this system evolve with respect to light, and if after I apply a second pulse again, depending on the time I let pass, I will have the system with a different phase, and then I'll be able to, okay? Very well. Okay, so now I want to move on, and I want to go to I want to include spontaneous emission. Okay. So how to include spontaneous emission? So how to include spontaneous emission? Does someone know the answer? Lindblad, yes, Lindblad is a good idea. Too complicated. I don't want to do Lindblad. So what you can do, yes, I'm going to put by hand. In the end, I'm going to put by hand. But because I don't have a quantized light, so I cannot really put spontaneous emission. So I'll need to do some. So just a second. So for spontaneous emission, can I do, if I have a two-level system, if I describe, there's something missing here, I can, so indeed, in order to include spontaneous emission, I think I have not done it right. Okay, okay, okay. So in order to include spontaneous emission, indeed, I needed to have my light quantized, so this I'll not do. So you believe in me, I'm going to put by hand in a certain set of equations, but in order to get the atom, in order to describe the state of the atom, such as to allow for spontaneous emission, I cannot anymore say that the state of the atom is a pure state like this. Why I cannot say? Because spontaneous emission now will induce decoherence. Spontaneous emission will induce dephasing. Spontaneous emission will add entropy to my system. Because when I have spontaneous emission, if the atom's in the excited state, for example, and the atom will decay with a certain time constant, and if I want to know the state of the atom in a time scale which is comparable to the time constant for decay, in this time scale, the atom will be either in fundamental state or in the excited state with a certain probability, and I really don't know in which state the atom is. And I'm not talking about a coherent superposition of the two states. There is no coherent superposition in this case. So when you have spontaneous emission, you have this is a quantum effect, but you have a probability of finding the atom in the excited or in the fundamental state, which is not, and this does not mean that you are in coherent superposition. This probability is in a way classical. This probability comes from the fact that you have added entropy because your atom is interacting with all the modes of the electromagnetic radiation. At some point, the photon escapes. You don't know to which mode it went. So you have some uncertainty about what happened. It's not an uncertainty because I don't want to talk about uncertainty because this is quantum. You have a lack of knowledge about what happened and when it happened. And this lack of knowledge means that you have added entropy to your system. Now, if you have entropy in your system, you don't know perfectly its state. So I cannot write this. So I will need to go to a generalized description of the state, which is called the density matrix, okay? So everyone have already heard about density matrices, or is it new for some people? It's not new for anyone, so I'm gonna go quick. So the density matrix, what's a density matrix? So, the density matrix, even if it's a matrix, it's a way of describing the state of the system. Okay? So it's not an operator. It's not, okay, it can be seen as an operator, but it does not describe a physical observable. We're talking about the state of the system. Okay? So density matrix to describe the state of the system. The first thing that we can do is, so the easy thing first is to describe the density matrix for a pure state. So if our atom is in a pure state, such as the state that I've written there, what's a pure state? A pure state is a state which you know perfectly. So pure state is a state with zero entropy. Okay, so any state that I can write like this is a pure state. So because I know perfectly the state, even if I don't know perfectly the outcomes of a measurement, because this is quantum mechanics, we need to accept its rules. But apart from that, this is a pure state. Then, a density matrix for a pure state is a matrix like that. This is the density matrix of a pure state, okay? So for example, I can write the density matrix of that state there. The cat of that state is just CGG plus CEE, and the bra of that state is CGG plus CEE, okay? And if I do the math, I find CG squared G plus CE CG complex conjugate E G plus CG CE G E plus CE squared E E, which I can also write in matrix representation, like this. And so here is the element that multiplies by E and gives G. So it's this guy, CG, CE. Here is the complex conjugate. And this is CE squared. So this is the density matrix for a pure state. But for a pure state, this is an overkill because a pure state, I can use the state. I can do quantum mechanics as I was doing before. Okay, but let's keep with this for a while to deduce the main properties. Okay. Now, so for the density matrix. No, okay, so let me already write, before I go into the properties, let me already write what's a density. This is the density matrix for a pure state. Now, let's suppose that my system is in a state which is a statistical mixture. So it's a mixture of classical, I have a classical probability of having one state and classical probability of having another state. Let's say that with probability P1, my system is in the state C1, and with probability P2, my system is in the state C2. So how will be the density matrix? Of course, if you have those two probabilities, must add to 1, otherwise it's not, they are not probabilities. If I just have probabilities of being in these two states, and then how is the density matrix? The density matrix is gonna be P1, C1, C1, plus P2, C2, C2. And in general, if you have Pj probabilities of being in J states, you can just add them all up. And in the most general situation, you can write the density matrix as the sum for J of Pj, Cj, Cj with sum of J of Pj equal to 1. Okay? This is what you can do. Very well. So then, okay. So now let's see how we work with the density matrix. So if I want everything in quantum mechanics, everything that I can predict is related to the outcomes of an observable. Everything that I can measure, and everything can boil down to calculating the average value of operators. Because if I want to know the probabilities of measuring something, for example, these probabilities can be seen as the average value of projectors. So in any case, this is everything I need to calculate in quantum mechanics in order to know what I measure. So for an operator, A, the average value of A, if the state is in the system, if the state of the system is described by the density matrix ρ, is just equal to the trace of ρ times A. Okay? Let's check this quickly. In order to check that this corresponds to what we expect from quantum mechanics, so let's suppose okay, so for checking this, what we're going to do is we will decompose. We will find the basis of eigenstates of A, of eigenstates. No, I'm sorry. A is not Hamiltonian. A basis of eigenvectors of A. So I have AI. So the operator A has AI eigenvalues and AI eigenstates. Eigenvectors, I'm sorry. Eigenvectors, such as the operator A can be written as sum. Okay, I is not good, so sum on G of AG, 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 okay? So those are just an orthonormal basis of eigenvectors. Orthonormal basis of our eigenvectors. You are going to say to me, oh, but if the eigenvalues are degenerate, yeah, okay, I just pick a base among the degenerate eigenvectors, and I do a orthonormal basis like this, okay? So if I write it like that I can calculate what's the trace of Rho A, okay? So the trace of Rho A, so Rho, I'm going to put Rho in this general shape. So this is just going to be sum on G of PG, CG, CG, times this is the operator sum on K, AK, AK, AK. Okay? Okay, so this is equal to, this is the trace of that. So this is going to be, so the sum with the probabilities Pj, since the trace is a linear operator, I'm gonna bring this, I'm gonna bring this outside. I can commute. So sum on J of Pj of the trace of this, and here the sum on K I'm gonna let it there. AK of, I need to do this calculation here. So this is CE AK. Yes, CJ AK. Okay, and okay, I'm sorry. Just undo. Yeah, I need also to decompose this one again. So I'm sorry, so I need to, I could have done it in an easier way. Now I need to include here again. So in order to arrive, I will need to include it here, the identity. So the identity, which is sum on L of AK, AK. Okay, so this is the identity, the completeness relation. I will need to include it inside here. So then I have, so this is going to be sum on J of Pj and trace of sum of on K of AK, and then if I include there sum on L of AL, and this I have CJ, and then I have here CJ, CJ is there, and then I have AK, okay? So this is going to be sum in J of Pj, trace of sum in K and in L of AK. This is just the coefficient of the CJ in the basis of A, so I'm gonna call this CL. Well, I can also as well keep it. So, and then I have also CJ AK. This is the coefficient of the CJ in the basis of the K, so this is this is CK complex conjugate. So I'm gonna write this. The CL is just the coefficient of CJ in the basis of the eigenvectors L, okay? And so I have sum on J of Pj, trace of sum on K and sum on L of AK, CK star, CL, and AL, AK. Okay, so if I take the trace, of this operator here, so you see that this operator is a sum of on K and on L of all diagonal and non-diagonal elements. So the trace of this operator here is just the sum of the diagonal elements. So this is just going to be, let me write it here, sum on J of Pj times sum on K of just the diagonal elements, so modulus of CK squared, so this happens for when L is equal to K, times AK, okay? So now what this is? This is just, so if CK is the probability for the state CJ to be found in the state L, this is just the value that I can find in the measurement AK with a weight which is the coefficient squared. So this is just the average value. I should have let a J somewhere, so J here. I should have let a J here. So this is just the average value of the operator A in the state J. So this is just equal to sum in J of Pj times the average value of A in the state J. And this is indeed can be interpreted as the average value of A. Now, see the difference. So this is the average value of an operator measured in quantum mechanics. And then I make just a combination with the weights given by the probabilities. So this is incoherent combination of probabilities. So this means that the states, each state can be in a superposition of states, can be in a superposition of eigenstates of the operator A, but the density matrix combine the states with a probability Pj, such as the final outcome of the measurement on this state is just going to be the combination of the outcomes in each one of the states with a probability Pj. So this is really to be interpreted. So this density matrix here with this operation here is to be interpreted as a statistical combination of different states. So this is just classical statistics, while each state can be in quantum superposition, etc., etc. Okay? So this is why the probabilities happen here. You have no cross terms, you have no coherences. This is an incoherent combination of states. So this is the meaning, this is how I can use my density matrix, and you see that now I have expanded my possibilities, and now I can also describe systems with entropy, okay? And I can describe systems with probabilities. So this is the density matrix. This is how I calculate the average value of an operator if my system is in the density matrix. And I also need another equation. You will believe in me. I need the von Neumann equation that describes the evolution of the density matrix. This is just given by the commutator between, now I don't want to inverse the order. I don't know if it's rho, I think it's H and rho. It's rho H. Be careful because it's the opposite way. Where is it? Where is it? I lost my notes. This is from yesterday from... Well, anyways, I have it here. It's H rho. It's different from the RMFS theorem, is opposed. Because this is not an operator, I mean, does not represent an observable, okay? Okay, so now I have my density matrix, and I will describe the state of my system. Yes? All density matrices are in this form. So this is the most general case for a density matrix. So you can, okay, what you can imagine is that you can, if you have a density matrix, you can diagonalize your density matrix, okay? And then you can write it in this way. And the trace of the density matrix must add up to 1 because of this. And all density matrices can be put in this way. Indeed, I have not told, okay, I have not shown, but this is, I have become from this expression here because this is, here is clear the physical interpretation, okay? But indeed, all density matrix can be put in this, cast in this way. And then you can interpret those states as the eigenstates of the density matrix, which are the pure eigenstates which are mixed. And this, in this way, this is also a technique. So if you take a general density matrix and you diagonalize it, the eigenstates of the density matrices are going to give you the probabilities, and then you're going to be able to calculate entropy. In particular, if you find just one p equal to 1 and the other is equal to 0, actually this is a pure state that can be hidden because the density matrix is complicated. Okay? Okay, so this is the way that we are going to use to evolve our density matrix. Now, for our two-level system, the density matrix is going to be, I'm going to just write it like this. Sigma EE, sigma E GE, oh, sorry, sigma GG, sigma GE, sigma EG, and sigma EE, okay? So from the general shape of the density matrix, this is the most general definition possible for a density matrix. From that, we see that first, the trace of the density matrix must be equal to 1 because I need to have the sum of all probabilities equal to 1. Okay, so it's a little more complicated because those states can be orthogonal, but in the end you can show that the trace must always be equal to 1. So the trace of the density matrix must be equal to 1. This means that sigma GG plus sigma EE must be equal to 1. And you must also have that if you take rho daga, this is going to be equal to sum of j of pj, cj, pcj, daga. Now, p are probabilities, so the complex conjugate of p is just equal to p, and the daga of this is this. So this is just equal to rho, so rho is Hermitian, and so this means that sigma EG is equal to sigma GE complex conjugates. So you see that actually you have just two numbers to determine, the other two are determined, okay? So how do I interpret for these two-level systems those numbers? So if I want to calculate, for example, the probability of being in the ground state, how do I calculate the probability of being in the ground state? The probability for being in the ground state is just going to be, it's the every time, this is the average value of the projector on the ground state. So this is the average value of this operator here. This is the probability of being the ground state. Now, I can use what I wrote. I can use this to calculate it. So this is just going to be the trace of my density matrix times G, okay? Okay, so I can do this in several ways. I can do this, I can write this in the Dirac notation, or I can just write this in matrix notation. So this is gonna be the trace of sigma GG, sigma GE, sigma EG, sigma EE times this matrix, which is the matrix 1, 0, 0, 0. So this is going to be the trace of, then you do the math. This is sigma GG, 0, sigma EG, 0. So the trace of this is sigma GG. So sigma GG is the population of the ground state. So this is the probability of being found in the ground state, even if I am in a situation where I have a statistical mixture, etc., even if I have entropy now. This is what I have. And you will believe me that if you calculate the probability of in the excited state, you will find a sigma EE, okay? So the diagonal elements of the matrix, the diagonal elements of Rho, they are called the populations. And in non-diagonal elements, those are called coherences. Why they are important? Well, they are important because, see, I'm going to show you the difference between two different states. So let's first think about the state, the pure state, G plus e to the I phi e over square root of 2, okay? So for this state, this is a perfect superposition of G and E, a coherent superposition because this is a pure state. You have a phase related to the superposition, okay? And so this state, the Rho is equal to psi psi. And this is just going to be, you see, if I do psi psi, I'm going to have JJ with 1/2. I'm doing quickly, so if you don't believe me, you can ask me and I'll do slowly. Then you're going to have EE with 1/2 also, because when you take the complex conjugate for doing the bra, this is going to disappear. The phase becomes the opposite, the complex conjugate, and then it disappears, so it's 1/2. Now, multiplying the term, multiplying the G, E, you are going to have e to the minus E phi. So this is going to be e to the minus E phi over 2. Is it true? Yes. And here, multiplying the EG, you're going to have e to the E phi over 2, okay? So you see that in this case, you have the coherences here, and the phase of the superposition is imprinted in the coherences. Now, if you have the state which is 1/2 G plus 1/2 E, the state represented by this density matrix, what's this state? What? Superposition, but it's not, this is also a superposition. Huh? With no phase. What does it mean with no phase? What? This is a Bell state? Oh, this is not a Bell state. This is Bell will be very sad about this because he'll be able to do no experiment with this. This is not entangled. This is first it cannot be a Bell state because we are talking about one only system. So, huh? Yes. There, now you got it right. First, we cannot talk about Bell states because for Bell states we need two systems. So here just we have one system, okay? And so we cannot talk about entanglement, even if it was a pure state. So we have no entanglement here. We have a superposition of states of the same system. Now here, you have an incoherent superposition. With 50% probability, the state is in G. With 50% probability, the state is in E. So how do I prepare this state? There are several possibilities, but one possibility is to take one G, take one E, make like this in your hand, and say to your friend, take one. And then your friend takes one. But he does not know, he, she, does not know who, which state they take, so this is the state they have. This is the maximum thing that they can affirm. Of course, one is in G, one is in E, but you don't know. Here, like, you don't know. You don't know. It's not a coherent superposition. Here is like, I don't know. With 50% of chances G, with 50% of chances E. This matrix is 1/2, 0, 0, 1/2, right? Because it's 1/2 here, 1/2 here, nothing in the non-diagonal elements. I have no coherences here, okay? So this is the meaning of the coherence, okay? Okay. Now, I was a little slow, maybe. I'll try to speed up a little bit. No, but I went to 40. Okay, I need to go to 45. Yes, okay. I'll calm down again. So, okay, but you understand then, so now I think what's important here is we are passing to a new description, which is density matrix. I want you to understand that this generalizes what I could describe. I can still describe the pure states, but I can describe more, right? So, like, this is a pure state. This is not a pure state. I could not describe this before. Now I can describe this, okay? And I want you also to understand the meaning of the diagonal elements, which are the populations. So you see, here and here, if I measure G or E, I'm going to have half of chance of finding G, half of chance of finding E, here or here. But here the state is in a coherent superposition. I'll be able to manipulate, to do some Rabi flopping, I don't know, Hadamard basis. Here, no coherence anymore. My qubit, no interest. Okay? Huh? The qubit is a bit, yes. It's a bit, it's not, I mean, it's not even a bit because I don't know which state it is. I cannot even use it, so I just... Oh, okay, then I measure, and then I discover, and then now I use. Yes, okay, it's a bit. Yes, okay. Say again? I mean, here you are in a quantum coherent superposition. Here, I would not say superposition. You can use, but it's not the word that we would use. Here, you are in a statistical mixture. So you don't know which thing you have. Here, it's important to say, here you know exactly what you have. The entropy is 0. Just it happens that for some measurements, for most of the measurements in quantum mechanics in a state, if you are not in an eigenstate of the operator you are measuring, the results are probabilistic. But this is entropy 0. Certain. This is not certain. This has entropy. I don't know this state. Okay? It's different. Yeah, I'm sorry? Yeah, because this is a probability combination. With 50% of chance I have G, with 50% of chance I have E, but this is not, I am in the coherent superposition that I created by doing a coherent pulse, etc., which I was discussing before, okay? Okay. So now, I want to make this system, which is the same system, evolve with the same Hamiltonian, but at some point I'm going to put spontaneous emission. And I'm going to put by hand. You will allow me to put by hand, because how do I really describe spontaneous emission? I should make a full model with quantized electromagnetic fields. Then I should put my atom to interact with the incoming light field, which I can let classical, but also with the quantized modes of light. Then, when my atom is in the excited state, it will be coupled by dipolar coupling also to all the light modes, and then this excitation can become a photon. And while this is happening, if I just look at my atom, I'm going to think that my atom is losing information because this becomes a photon that I don't know where it went. Okay? This is how I should really do to include spontaneous emission. But I know the result of the calculation, and then I'm going to put one term, two terms actually there, and you're going to believe in me that this is what happens if I do the full model. Okay? And then you're going to look at the consequences. Okay? Do you allow me to do this? Okay, so let's do this. And then I will begin in the same way. I have my Hamiltonian, which is just the same. So h bar, 0, h bar omega 0 cos of omega t, h bar omega 0 cos of omega t, and h bar omega 0. Okay, so this is my Hamiltonian. And I want to calculate this. So I need to calculate this commutator, okay? So what's the commutator? This is equal to this matrix, okay? The Hamiltonian times sigma E, G, sigma G, E, sigma E, G, sigma G, G, minus rho, which is sigma G, sigma E, G, E, sigma E, G, sigma E, E, times the Hamiltonian, which is that matrix there, okay? And you need to calculate this. So you're going to have a matrix with 4 elements. And if you divide by EH bar, you are going to find the derivative of each element of the matrix, okay? You understand what we need to do? Okay, so do you allow me to put the equations already ready? Okay, so I'm going to do this. So you're going to find a set of 4 equations. So you're going to find that the derivative of sigma GG with respect to time is equal to, have I let, they are here. It helps a lot. So this is going to be okay, and I want to do something else. I'm sorry. You're going to move this, change this here, okay? What I want to do is the following. So it's the same Hamiltonian, but now I will let it depend. So I will come back with the center of mass because I'll be preparing to include the center of mass as a, okay? Okay? Okay, so the equations are going to be the following. So I'm going to write dEE over time, EE minus eta times. And then the cos, you can write cos of, let me write this down, cos of phi equal to the E phi plus e to the minus E phi over 2. Okay, so I'm going to do this, and this is why I'm going to have here E kr minus omega t plus e to the minus E kr minus omega t. That multiplies sigma GE minus sigma EG, and you have dE dt equal to minus E omega 0 over 2 e to the E kr minus omega t plus e to the minus e kr minus omega t sigma e minus sigma g plus e omega 0 sigma ge. Okay? And I am not writing down the four equations because since I know that sigma g plus sigma e, they are always equal to 1, the equation that I will find, and you can verify, if I derive this on time, I find this. This means that the sigma gg, the derivative of sigma of the population of the ground state, is minus the derivative of the population of the excited state. Okay? In the same way, if I remember that the coherences are one the complex conjugate of the other, you can find that derivative of sigma eg must be the derivative of the sigma ge complex conjugate. So you can find all four equations, but you don't really need to solve them. We just need to solve those two, okay? Very well. Now, here we have the same situation as you had before. We have some terms that turn fast, some terms that do not turn fast. But it's hard to recognize it there. So what I will do again the rotating wave approximation, okay? So now, here the rotating wave approximation is a little different. Remember that for the other case, the rotating wave approximation in the pure state, what we did was we replaced the coefficient of the excited state by a coefficient which was equal to this times a phase which is now plus or minus, I don't remember. If someone have the notes can tell me, otherwise I'm going to search. It was minus. Thank you. Minus. I find a plus. It's just that maybe I wrote in the opposite. I find a plus. I wrote CE prime with a minus. Now it's C prime, C. Okay, so we have done this, right? Okay. Now, I'm going to go, what I need to do. Let's think quickly about the pure state. In the pure state, if my density matrix is in the pure state, first, sigma gg in the pure state. So in pure state, sigma gg is equal to cg squared, so this is going to stay the same. Sigma EE is equal to modulus of CE squared. It's always going to be the same, because modulus squared, the phase disappears. Now, sigma GE, sorry, this was equal to, this is in the GE, so the E is the cat, so this is equal to CGCE complex conjugate, okay? So this will become CGCE prime complex conjugate, if I pass this there, e to the minus e omega t, but complex conjugate e omega t, okay? And if I call this sigma g e prime, so then I have the relation, okay? And since the other one is the complex conjugate, it's going to be with a minus, okay? Now this is for pure state, but for any state I'm going to do the same. So this is just to justify to you what I should do, and then for going to the rotating frame of the light. So let us go to the reference frame rotating with omega. So this means that we have then we have sigma GE prime equal to e to the minus e omega t sigma GE. So let me just check if I get this right. Yes, it's good. sigma EG prime equal to E omega t sigma EG. So this is a transformation we need to do, okay? Then I can replace this inside the equations, do the math, and I'm gonna find well, I can write the big equations and then we do the approximation, okay? So, the big equation is going to be derivative of sigma EE with respect to time equal to minus E omega 0 over 2 e to the minus e to the E KR minus omega t plus e to the E KR minus omega t. That's going to be multiplied by sigma EE. No, I'm sorry. So this is, okay, it's multiplied by E omega t sigma GE minus e to the minus E omega t sigma EG prime. And then you have d sigma GE prime equal to minus E omega 0 over 2 e to the E KR minus omega t plus e to the minus E KR minus omega t. That multiplies sigma EE minus sigma GG e to the minus E omega t plus E omega 0 minus omega sigma G E prime, okay? So here this omega appears because now if I derive this equation, I have two terms, remember? And then this is why I have this omega that happens here, okay? And so this is delta. And you see that now here I have terms rotating with e to the minus 2 omega t terms that do not rotate. I have terms that rotate with 2 e omega t, do not rotate, do not rotate, rotate with minus 2 e omega t. So now we do the rotating wave approximation, which is replacing e to the plus and minus 2 e omega t by their average value, which is 0. And then we get the total equations, which are independent of time, which is nice. G sigma GE prime. Let me write them in the other. So this is oops, no. Sorry. Okay, so this is actually here is minus delta, right? Because delta is omega minus omega 0. Now, okay, nice. I complicated everything. Up to now, I complicated everything for nothing, because here I have no spontaneous emission. So here, if I solve this problem, I will still get a pure state. I just did some complication for staying in the same situation, more complicated. Well, okay, nice. Now, I can include spontaneous emission. How do I include spontaneous emission? The first obvious effect of this spontaneous emission, again, this can be done in a very rigorous way, which is not what I'm doing here. I'm putting the terms that you would deduce in a rigorous way, okay? Now, intuitively, what do you expect from spontaneous emission? One, you expect that the population should go down. So, in the equation for the excited state population, I would expect, in the absence of laser excitation, to have an exponential decay, okay? With a rate which is gamma, the spontaneous emission rate. So how do I put spontaneous, I put exponential decay? I just do this, okay? So by doing this, if I don't have laser excitation, for example, the solution is sigma EE equal to sigma EE0 e to the minus gamma T, right? The solution for this first order. Yeah? In this term here, to the ground state, you mean? Yeah. But so what's important is the population. So you see, so here, imagine, let's take a look in this equation here with no, so omega equal to 0, so no laser excitation. So, you understand? Okay, and so you're going to have sigma EE equal to sigma EE0 e to the minus gamma T, okay? What's interesting is that if you calculate with the equations there, the derivative of sigma GG on time, you're going to find that this is plus gamma sigma EE. Depends also on the excited population. Because you should not evolve if you don't have excited population. Okay, so it's sigma EE that appears on both with opposite sides, okay? And of course, this also. Okay, and the coherences. So the coherences, the spontaneous emission will also have impact on the coherence. Will also have an impact on the coherence. You can imagine that if you begin in a superposition, coherent superposition, you have some coherences, and if you decay, eventually you don't have any more excited population, you should not have coherence anymore, neither. So you must have some decay on the coherence also, okay? And you can show on this very rigorous model that the coherence will decay with a different rate, okay? That I'm calling small gamma, okay? So, big gamma is spontaneous emission. Rate. For rubidium, do you work with rubidium? How much is gamma for the D1, D2 lines? For the D1 line. For the D2, no, everyone with the D2 line. Yes, 2 pi times 6.05 megahertz, yes. Some of you work with strontium. So for the large transition of strontium, 1s0, 1p1, 2 pi times 30 times 5 megahertz, okay? Strontium have some narrow transitions also. For example, the 3p1, so this is 1p1. So 3p1 has 2 pi times 7.4 kilohertz. Okay? So it's a narrow transition. Okay, so who is small gamma? Small gamma, so the coherence can decay by several reasons. One of the reasons for the decay of the coherence is because of the decay of the excited state population. So the minimum value for gamma is equal to, small gamma is equal to big gamma divided by 2. If you just have spontaneous emission as a dephasing process, this is what you should have. Now, you can have other kinds of processes in your sample. You can have collisions between atoms. Collision is a typical low energy collisions do not change the populations. So the atoms come and go, and if they are excited, they continue excited. If they are in the ground, they continue to be ground. But if they are in the superposition, during the collision, you can have a shift on the energy of the levels. This means that the phase of the excited state will go faster or slower with respect to the phase of the ground state for a short period of time. This means a phase difference after the collision. Now, if the collisions are random, you approximate more or less, depending on your kinetic energy, depending on your velocity. This means that you have an added phase which is random. This contributes to the decay of the coherence and not of the population. So I would add only here an additional dephasing rate, because this is dephasing, because this is acting only on the coherence due to collisions, for example. Okay? If you have random magnetic field or a magnetic field oscillating on time, this will not induce decay, but this will make the energy of the levels to fluctuate in a random way. So you can have noise due to magnetic fields, etc., etc., etc. So you have several effects that can dephase your superposition, but will not cause population decay. So those would be entering here, okay? I will not be considering. From now on, we'll just take here, okay? But you in general, you may need to think about other effects, okay? Okay. Now, what we're going to find with these states. So you see these equations, well, they are not simple. We are in a two-level system already, difficult equations. You have, in general, you have 4 frequencies, 4 rates, omega 0, gamma, delta, big gamma, small gamma. Okay, small gamma becomes big gamma, but still have 3. Analytical solution, not easy, okay? Not easy. Okay. I can show you. Okay, maybe it's in the end of the class. In the beginning of the next class, I'm going to show you some numerical solutions of this equation, okay? Now, what we're going to do is a different thing. So, in general, you can still do Rabi oscillations, you can still operate with your system, but now you have those decay mechanisms that are inducing entropy in your system, and will make your system tend to a stationary state. Every time, due to those dephasing mechanism, this decay mechanism, the system goes to a stationary state. So now we're going to obtain this stationary state and try to see how it behaves. What are the main properties of this stationary state? Okay? How do I get the stationary state? If a set of dynamical equations have a stationary solution, how do I get the stationary solution? Yes, exactly. So, to get the stationary state, sigma E equals to 0, d dt of sigma E g prime equal to 0. Okay? If you do this and you do the math, I'm not going to do the math with you because I really want to interpret a little what we get. So if you do this, make this equal to 0, you see you can. I'll just give you some hints on. Okay, we are here actually. I'll just give you some hints on what you should do. So the first thing is that here you see you have sigma GG, but you can put this as 1 minus sigma EE, because the sum of 2 is 1. So you need to replace this by sigma GG. And so then you will need to write also the equation for sigma EG, because it appears here. And actually you'll have a set of 3 equations, okay? And then you need to solve 3 equations, 3 variables, and you do the math. You know how to do this. Is a linear system, and you get the answer in the end. Can I give the answer? Okay. Where is the answer? Here is the answer. So the population of the excited state in the stationary situation, so after a long time. So what's long time? T much bigger than the decay rate, okay? So for T much bigger than the decay rate, nothing evolves anymore, and you are in this situation here. So the population can be written as 1/2 of this saturation parameter, okay? S is the saturation parameter. So this saturation parameter is equal to 1/2 of omega 0 squared divided by delta squared plus gamma squared divided by 4. Let's work a little more with the saturation parameter. So something important for us will be the saturation parameter in resonance. So the resonant saturation parameter, resonant saturation parameter is just the saturation parameter when delta is equal to 0. So this is equal to S0 equal to 1/2 omega 0 squared divided by gamma squared divided by 4. So this is 2 omega 0 squared divided by gamma squared, okay? So this is the resonant saturation parameter. Now, remember that the Rabi frequency depends on the electric field of the incoming light, okay? So, but something else depends on the electric field of the incoming light, which is the light intensity. So what's the light intensity? The intensity of the incoming light. How do I describe what's intensity? Do you know? How the experimentalists measure intensity of a beam? In milliwatts per centimeter squared. No, if you go to the lab and measure in milliwatts per centimeter squared, intensity is energy per time and per area, or power per area, okay? So it's the flux of energy. So it's the flux. A flux of something is something per time and per area. So flux of charge is charge per time and per area. So the intensity of light is the flux of energy, is the energy flux. Okay, so do you know an expression as a function of the electric field for the intensity of light? The intensity of light is going to be equal to the modulus of the average Poynting vector. You know the Poynting vector. So this is the Poynting vector. Which is equal to the max amplitude of light divided by 2 the magnetic permeability and C, okay? So this is light intensity. Okay, now I want to make the light intensity appear there. And then for that, I will remember that omega 0 is equal to d scalar is 0 divided by h bar. Now, you will believe in me, for a dipole, so this is the dipole of the atom, which is excited by the incoming electric field. So we have not discussed about polarization of light, etc., etc. But in classical terms, an induced dipole is always in the direction of the electric field. So you're believing me if I pass from here to this because they are both in the same direction, okay? And then we can discuss about polarization, and you'll see what the light can do to the atom and how we can calculate the dipole, and really the dipole is the same direction. So this means that the electric field squared is equal to h bar squared omega 0 squared divided by d squared. And if I put this inside there, I find that this is equal then to h bar squared omega 0 squared divided by 2 omega 0 c d squared, okay? And then I can isolate omega 0 from here and put it inside. And I'm going to find the saturation parameter as a function of the light intensity. So the saturation parameter is equal to, so if I put, I invert this, I put it inside, I'm going to find that this is equal to 4 mu0 c d squared divided by h bar squared gamma squared times the light intensity, okay? That I'm going to write just as the intensity divided by an intensity that I call saturation intensity. What's the saturation intensity? The saturation intensity is the intensity of light that I need to send to make S0 equal to 1. Okay? So, this is the saturation intensity for light, for the atomic transition. So each atomic transition has its own saturation intensity. Okay, so the saturation intensity here is just equal to h bar square gamma square, sorry, divided by 4 mu0 c d square. Okay, this is the saturation intensity, and I'm gonna give you, I'm not gonna justify, but I'm gonna give you another expression for this saturation intensity that you will find it to be useful. If I use, there is a relation, you know, the decay rate I have put by hand. I cannot calculate what the decay rate is because I have not done a full quantum model. But if I do a full quantum model, I realize that the decay rate, since the decay rate is related to the dipolar coupling of my atom with the electromagnetic modes of light, it will be related to the dipole moment of my atom also. And I have an expression that I cannot deduce, but I will give to you between the dipole model and the decay rate, which is just this. This is the expression. And if I put this inside, you can have another nice expressions for the saturation intensity. One of is this. Another one is this. Pi over 3, h, not h bar anymore, h c gamma divided by the wavelength of the transition. So you see, you can write the saturation intensity as a function of parameters that you know in the lab. The decay rate and the wavelength of the transition. Okay? So then you can calculate in your lab. It's a little more complicated than that. This is going to give you an order of magnitude. It's not going to give you exactly the saturation intensity. Why? Because this model we are doing is for a two-level transition. Now you go to your lab, you work with rubidium, you work with potassium, and then you have spin on your electron has spin, your nucleus has spin, and so you have magnetic moment. You have the Clebsch-Gordon numbers to give weights to the transitions. In the end, you will have probably a numerical factor of the order of 1 multiplying this expression, okay? So this is to be taken in this sense. You're going to have an order of magnitude, but not really, okay? Because of that, because of the Clebsch. For strontium, it works perfectly because we have no magnetic moment. Sorry for the alkaline people. So, okay? Yes? Simulated emission. Simulated emission is okay. So the simulated emission in this model, how you'll get it? Your atom, let me think for 1 second. Okay, so for understanding spontaneous emission and simulated emission, so for understanding spontaneous emission and simulated emission, you need to put the quantized modes of light. And then you need to calculate the coupling between your atom and the light. And you're going to see that in the coupling, you will have a term which is proportional to, because simulated emission is related to the light intensity, but you need to, so you are going to see that you have two kinds of coupling. You have, your light has destruction operator and annihilation operator and creation, yes, creation and annihilation operator, thank you. So you're going to see that the probability to the term that describes the probability of absorbing one photon is proportional to this. So this means that the probability for absorbing is proportional to this, and for emitting is proportional to this, for emitting one photon. So it's proportional to the number of photons, and there is this one. So this means that here you are describing the spontaneous emission, and this, when you have some photons in your mode, you have an increased probability for emitting one photon, and so this describes the simulated emission. So when you already have photons, you can emit more. So the probability for emitting is proportional to this. And you can show indeed that the ratio between spontaneous and simulated is the saturation parameter or proportional to the saturation parameter. But you really need to go to this quantum model to understand this, because you need to put photons and understand, okay? It's the coupling, emission, spontaneous or simulated, is happens when you have coupling between the state of your atom and the state of your, oh, I have passed the time. So, and the state of your light, okay? Well, okay, so I will not extend. So I will stay here, but we need to continue discussing about this solution. I'll do this next time, okay? So we come back at 11:15, okay? So let's take the 15 minutes, but not the 5 minutes I took more, otherwise we